Bismillahirrahmanirrahim. Today we will discuss heat capacity and latent heat. The first slide shows the configuration of the oxygen tank, where you can see the pressure of the tank is around 7 bar, and then it's being transmitted to the system outside the tank at 4.1 bar. And you can see what we call the pressure reading vaporizer, which is used in certain circumstances where the pressure is being decreased for too much taking oxygen from the top of the cylinder speedily. So we must compensate for the latent heat of vaporization, decreasing the temperature and hence increasing the vapor pressure. So this is a compensation method used to support the the system with additional vaporized oxygen to overcome the increased saturated pressure from the increasing temperature. And then we can see the state of the matter, solid and liquid and gas, how being changed between melting and boiling and condensation and freezing and subliming. All this subliming means changing the solid to gas, and this is the EMO apparatus, Epstein Macintosh Oxford, where there is a water jacket. We will use the high specific heat of water in trying to save heat for this system of anesthesia. The first slide will show the two important definitions, which is the specific heat capacity and the heat capacity. What the meaning of specific heat capacity is the amount of heat required to raise 1 kilogram of a substance by 1 Kelvin. The units made of 3 parts: joule for kilo and for Kelvin. 3 parts confirming the unit of the specific heat. So this is the amount of heat required to elevate specific heat. The heat capacity is the amount of heat required to raise the temperature of the given object by 1 Kelvin. So we will remove the kilogram from this unit, so it will be joule for Kelvin. Sometimes, of course, we use Celsius instead of Kelvin because Kelvin is commensurate with Celsius. So we can use Celsius in definition. Clinical application or to show the heat capacity, and of course in vaporizers, the components of vaporizer, whenever they add to each other, each of them has a special heat capacity to preserve heat. So this is one of the main important items during functioning or during constructing a vaporizer, to have its substance made of copper or bronze to preserve heat. The tissue-specific heat capacity, which must be noticed, is 3.5. Now we begin to say kilojoule for each kilo and for each degree Celsius. So we are here using Celsius as we did before instead of Kelvin. So these are the 3 parts that confirm the specific heat of the human. And if the human, of course, as a standard is 70 kilograms, the total heat capacity will be around 245 kilojoule for each degree Celsius. I'm sorry, the power of -1 is being put downwards of the figure, so you'll notice that. The third point, when the temperature of the human being has fallen to 36, of course the human being compensates by shivering. This shivering increases the basal heat capacity of the human being from 80 up to 320 watts. This is what is required to increase the temperature. So we are increasing the figure for 4 parts to reach. Of course, this difference whenever, of course, it is joule per second. So whenever I want to figure it out in minutes, I multiply by 60. So this will yield the amount of heat required to elevate the temperature of the patient whenever his temperature increases to 36. So if we figure it out, we can find that the patient ought to shiver for 17 minutes to gain this difference in temperature. You see? Of course, whenever we mention the temperature, always we consider the mean body temperature, which the difference or the mean is the calculation between the shell and the core temperature. The specific heat of water is 4.18 kilojoule for kilo or each kilo and for each degree Celsius. This the biggest or the largest figure for specific heat among liquids. 4.18. 4.18. 1 calorie equals 4.18 joules. So you must, of course, mention that was the meaning of calorie and the correlation to joule. In dietetics, people working in diets, they consider the kilo calorie, which is 1,000 calorie, written as C capital. This denotes that it is, of course, a kilocalorie. The specific heat of both substances are less than water. Okay, so if suppose we have 2 liters of blood or 2 kilograms of blood, and they are stored at the degree of 5, and then we want to elevate it to the 35. You see, so there is a difference of 30 degree. Whenever I want to calculate the amount of heat required to elevate this temperature of blood, I multiply, of course, the amount times the specific heat of blood. We can see that is much less than the specific heat of water. And whenever we multiply, we yield a figure of course in kilojoule. This figure will aid the load on the human being. It will may decrease the temperature of it by 1 degree. So we must have a method to warm this blood to avoid the hypothermia that can be yield from transferring this 5 degree blood. Of course, this is the specific heat of water. Whenever I increase the temperature of it 1 degree, I ought to support by 18 kilojoule per kilogram per degree Celsius to elevate the temperature of it. Suppose 1 degree from something to another one. So I apply this amount. Gases have a very low specific heat. 1.01, almost 1 kilojoule for each kilo and for each degree Celsius at a constant temperature. Of course, whenever I mention gas, it's better to use volume, liter. So it's better to be confirmed or transferred to be 1.2 joule. Imagine the joule, not from kilojoule, for each liter for each degree Celsius. So this is the specific heat of air. You see, so it's almost 1/1000th of the figure we mentioned before. What's important of it, of course, that means that the gas gain heat very speedily and lose it very speedily, and this is a good advantage whenever the person smokes. This smoke, of course, yields hundreds of degrees of temperature whenever they reaches the mouth and the upper airway, because they have a very low specific heat. They lose this temperature, reaching to the body at almost the normal human tissue, the human temperature. I'm sorry. So we have a minimal amount of heat required to elevate this amount of air. In the tube system of anesthesia, of course, the gases always are transferred from the vaporizer cooled. So whenever they reach the human tissue from the anesthetic circuits, they lose the temperature and they gain temperature and then they reach the human being almost at their normal temperature, unless we use humidifiers. Of course, this is what I meant by exclamation mark. That humidifiers are being used to keep the temperature and avoiding hypothermia, especially in kids. Heat loss, of course, from inspired gas can be figured out by the flow in the specific heat capacity times the temperature raise. So I want to raise the temperature, suppose, of the gas coming from the vaporizer from 20 to 34, so it's 14 difference. So I multiply and I yield around 2 watts. See, so this is what is required to elevate the air entering the human being. You see, for warming, almost 2 watts is required. The third definition is the latent heat. What's the definition of it? When the substance changes from a liquid, suppose, to a vapor, or from a solid to liquid, and so forth, heat must be supplied at a constant temperature. So we have to have a support of heat. Latent heat, we have latent heat of fusion, when a solid changes to a liquid, and also it can be called melting. A salt from a liquid, latent heat of crystallization. This yields temperature, gives temperature. And we have, of course, the most important latent heat of vaporization, which is very important for anesthetists. So specific latent heat is defined as the heat required to convert 1 kilogram of the substance from one phase to another at a given temperature. Don't forget to say at a given temperature. Whenever I want to mention a gas, I must incorporate temperature. The systemic international is made of 2 parts: joule to each kilogram. Joule for 2 parts, confirming the unit of the specific heat. What are the applications or the items correlated to specific heat? Water at 100 degrees Celsius during the boiling point is it's converted to steam at also 100. So the supplying quantity of heat is 2.26. You ought to remember it, memorize it. 2.2.6 mega joule for each kilo. These are the 2 points that represent the unit of specific latent heat, and we are now talking about the mega by mega. You see, so this is the amount required during the boiling, whenever the temperature reaches to 100. For instance, if I want to vaporize this amount at the normal body temperature, we will yield, of course, more. We will be in need of more megajoules. So it's, instead of being 26, it will be 42. So this is the difference between the specific heat capacity whenever the temperature is at 100 or at the 37 degree of the human being. So the lower the temperature, the more latent heat is needed. And this is the figure will show the difference between the heat required to elevate or to transfer the liquid to vapor in the 2 circumstances, whether it's at 100 or 37. Of course, nitrous oxide at 36.5, which is the critical temperature, is transferred to vapor without additioning of temperature. You see, from the curve, you can see that no temperature is needed whenever it reaches the 6.5. You see, it changes spontaneously without aid. Latent heat in anesthesia. So we're going to mention several points. The first point is vaporization of fluoride. Of course, it's been put in a special bottle, and it's under pressure so that it will be kept in a liquid form. And then by inducing a shift flow from it, we will induce cooling. This cooling is capable to induce energy, so it's being used to remove, suppose, an abscess or a wet loop. Of course, most modern anesthetics are supplied by a compensator for this heat changes, so to keep the saturated vapor pressure, as we mentioned before. If the nitrous oxide cylinder, as we can see in the next figure, if the nitrous oxide cylinder is being opened fully and rapidly, we will find the process of vaporization decreasing the pressure inside the cylinder. So whenever I close it, as you can see, whenever I close it, the pressure is yielding, this curve is going downward. So whenever I close the valve at that line, we'll find that pressure will increase again in this dotted form here. Of course, carbon dioxide and cyclopropane are being prepared as liquid in cylinders, and they don't need much of temperature to be transferred to vapor, so it's not much important in anesthesia. Of course, the most important thing is the oxygen cylinder. As you can see, we are trying to use oxygen to minimize the cost. We know that the critical temperature of oxygen is around minus 116. So this is the oxygen tank where oxygen is being liquefied. It has been put in a gigantic flask. This flask is capable to induce a vacuum. This vacuum is capable to keep the temperature, and then oxygen is being transferred from the top of it into the pipe system. The temperature of this tank is around 7 bar. Whenever it comes out from the system, is very cool, so it must be supplied by a superheating cooler. As you can see, this superheated cooler is being transferred to the system, and there where the pipe system is always 4.1 bar, and whenever this tank is being taking too much of oxygen, the latent heat of vaporization will increase, so it will decrease the temperature inside the flask. Of course, it will affect the process of vaporization, and it will affect the pressure. It is going to be sensed by what we call a pressure raising vaporizer. Whenever the pressure is decreased, so it will increase the flow through this vaporizer. This vaporizer takes additional oxygen and warms it and causes vaporization of it, supporting the system additional to compensate for the decreased temperature yield from opening the oxygen tank speedily, very speedily. On the other hand, if the tank is being left for around 1 week, the pressure inside it will increase. You see, so we have to have what we call a safety valve to guarantee against increase in pressure. Latent heat latent heat and heat loss from the patient. Of course, as we said before, for warming the air, we need around 2 watts. And if we want to humidify this dry gases to reach 34 milligram per liter as that present upper airway, we need extra heat, of course, for this air. which will be taken off from the 80 watt of the human being. So whenever I want to figure out the amount of heat required, I multiply for the specific heat of vaporization of water. It comes from the mucous membrane of the human being, and then I multiply by at that temperature, of course, by the total water required, which is 30 milligram per liter. Of course, I don't know how many liters are being. So all these are the amount of water needed. It will take as much as 11.6 watt, you see, from the 80. So it's too much, you see. This figure, of course, is more than what we mentioned before in chapter 9, because the dry gases which are being taken from the vaporizer during anesthesia are much more dry than what we had mentioned before. This is why instead of we utilize 10 watt, this circumstances we take off around 11.6 watt. This is the difference, you see. And the old closed anesthetic system, we use what we call Walter's canister. It is a special closed circuit. It was a method to conserve moisture and heat. And sometimes we used to put the patient in circumstances of a wax bath, and it was being used in treatment of cancer. It is a simple subject, and most important thing is to know the definition of the specific heat and the latent heat and the specific, the specific heat and the heat capacity and the specific latent heat and the applications during anesthesia. والسلام عليكم ورحمة الله وبركاته.